Hello class, welcome to the lesson 7.3 review for geometry. So we're going to go ahead and get started with the problems here. So the lesson is about proving whether or not each of these is a parallelogram. And you can easily do this if you if you have the theorems in your notes. But we're going to prove it kind of rigorously as well, just so you can kind of see the why. All right, so number one, this one is definitely a yes. It can be proven to be a parallelogram, and the reason is it's one of the theorems in your book that says if you have, since you have one pair of opposite sides is both congruent and parallel. All right, so yes, but we're going to prove this rigorously. Okay, I'm going to do this over here, just off to the side, so you can understand the why. Okay, so I'm essentially doing a proof of that theorem. Okay, so first off, if you think about it this way, if you divide a diagonal here, then you have, okay, this side is reflexive to, it's congruent to itself by the reflexive property, and so we got ourselves two sides here. And because we know that these are parallel, that means that this angle must be congruent to this angle. And so we can see that those two triangles must be congruent by side, angle, side. We can see we got a side here, an angle, and a side. And so these two triangles are congruent, and therefore these opposite sides must be congruent as well, because by CP/CTC, if those triangles are congruent, then those sides must be congruent as well. So that's called CP/CTC. Corresponding parts of congruent triangles are congruent. So therefore opposite sides are congruent, and therefore it must be a parallelogram. In addition, we can also say we can also prove this a little bit further and say that these sides must be parallel as well, the top and the bottom. And we can do that by looking at another diagonal. So if I look at this diagonal here, then notice that in this case we would have another pair of alternate interior angles there, right? And so we can see that this triangle and this triangle must be congruent by angle, side, angle, ASA. And then therefore if those are congruent, then that means these this is congruent to this, and then this is congruent to this, okay? But then we know that means that the top and the bottom ones must be congruent by side, 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 right? And therefore this must be congruent to this, because those are the ones that correspond, and therefore we have ourselves parallel. Those sides must be parallel by the converse of the alternate interior angles theorem. Okay, so then we've proven that we have two pairs of parallel sides. Okay, I know that's a lot, but I did want to explain the why. Now this one is a yes as well, because one of the theorems in your book is that if you have two pairs of opposite angles are congruent, which that's what you have, two opposite angles, two pairs, I mean, are congruent, and that's the case. So this is a yes. So let's prove that a little bit more rigorously. Okay, so since so first off, we got these opposite ones are congruent, and so what we can do is if we know that the angles in a parallelogram add up to 360. That's because of this formula, n minus 2 times 180, right? And so we get 4 sides minus 2 times 180, and that's going to give us 360. So we know that these angles must add up to 360, right? And so let's call this both x, and let's call this both y. All right, so we have that those are x, and those are both y. They must be the same, but we also have that these angles must add up to 360. So let's add this up. So we got x plus y equals 360, right? So we get 2x plus 2y equals 360. And so what that tells us is that, okay, if I divide both sides by 2, then that's going to cancel these out. And I get x plus y must be equal to 180. All right, so that's saying that these add up to 180. Well, if that adds up to 180 and this adds up to 180, then what does that mean? That means that, so what it means is that this must be parallel to this side, because these two add up to 180. That's the converse of the consecutive interior angles theorem. And then this side must be parallel to this side, because these two on top add up to 180, and that's the consecutive interior angles. And therefore we've proven that we have two pairs of opposite sides that are parallel, and therefore it has to be a parallelogram. Okay, so there's the more rigorous proof of that. Number two, this one is no, right? We can't, there's not enough information. We only have one pair of congruent sides. We need another pair, so we need more information. So even if we try to break it up into two triangles, we have, this is congruent by reflexive property. We have two sides, but we have no angles or anything to prove that the triangles are congruent. So there's just not enough information here. Part B, this is true because opposite sides are congruent. So yes, we have two pairs of opposite sides are congruent. And we're going to prove that again more rigorously. This is a really bad parallelogram, sorry. So we're saying this is congruent to that, this is congruent to that. So if we break this up here, we can see that these two triangles must be congruent by side, 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 right? Well then if that's true, well then this angle must be congruent to this angle, right? Well, and if that's true, then this has to be parallel to that. So so let me go back and explain that. So if these two triangles are congruent, then by CPCTC, those two triangles must be congruent because they correspond. And they're also alternate interior angles. So by the converse of the alternate interior angle theorem, those sides must be parallel. And then similarly, because the two triangles on the left and right are congruent, that means that this side has to be congruent to this side right here, or this angle has to be congruent to that angle by CPCTC, and then therefore this has to be parallel to this by the converse of the alternate interior angles theorem. All right, and therefore it's a parallelogram because we have two pairs of opposite sides that are parallel. All right, so that's more rigorous there. So now number three, determine whether each is a parallelogram and justify your answer. So in a parallelogram, yeah, this is a yes. So let's go, let's write that out. So yes, one of the theorems was that the diagonals bisect each other. Okay, so we have the diagonals bisect each other. So that's the theorem, that if you have a quadrilateral with diagonals that bisect each other, then it must be a parallelogram. Again, this can be proven as well. We know that by vertical angles, these two must be congruent by vertical, and we have side angle side, and therefore these two triangles must be congruent. And then therefore, if they're congruent, then that means by CPCTC, those have to be congruent. And then similarly, by vertical angles, those must be congruent. And so we have side angle side for the left and the right triangles. And then therefore these sides have to be congruent by CPCTC. Opposite sides are congruent, and therefore we've proven it that it's a parallelogram. And we can use the argument from here that we did here to prove that we have parallel sides. Okay. All right, so number four, determine whether each is a parallelogram. So same thing here. We have opposite sides are congruent, but then the other opposite side, we don't know if it's congruent, but it's parallel. So this is no, not enough information. So how do we know it's not enough information? Well, if we try to divide it this way, then we know that because these are parallel, we have alternate interior angles, And so we have angles there. But note that in order to prove, note that this side must be congruent to itself by reflexive, right? And so right now we have ASS or SSA. But remember, that's the mule trap, the donkey trap that I call. That's not enough information to determine whether the triangles are congruent. And therefore, we cannot say that the triangles are congruent because we don't have enough information. And therefore, if we can't establish the triangles are congruent, then we can't establish CP/CTC. And therefore, we can't establish parallelogram properties that we need to establish. So not enough information. All right, so I know I went over a lot of details there, but I figured this is the place to do it, just to get some extra information. All right, so problem set number 2. This time we're going to say, okay, how do we solve for the variable so that we can make sure that it's a parallelogram? So find the values of x and y so that the trays and hinges of the organizer form a parallelogram. So you can see this like parallelogram shape. Well, remember that the opposite angles in a parallelogram are congruent, right? So they have to be congruent for this to be a parallelogram. So we're going to set those equal. 3x minus 4 equals 2x plus 16. And then we got 4y minus 56 equals 2y plus 34. We could solve this. So we're going to add 4 here and then subtract 2x there. And then for this one, we're going to subtract 2y and then add 56. So we get x equals 20. And then we get 2y equals 90. 34 plus 56. Cut that in half to get y is 45. Okay, number 2, find the value of x and y so that it is a parallelogram. So remember, if this is a parallelogram, the diagonals must be congruent. Okay, so you set those equal. So we get negative 4x minus 2 equals negative 3x plus 4. And we also get 3y minus 5 equals 2y plus 18. So set those diagonals equal, and then we can solve. So we get plus, so I'm going to add 4x to both sides because that's a negative 4x. And then I'm going to subtract 4 here. All right, so we get negative 6 is equal to x. All right, so we get negative 6 equals x. And then here I'm going to subtract 2y, and I'm going to add 5. Okay, so we get y equals 23. Okay, and then number 3, remember that opposite angles must be congruent. So this must be congruent to this. This is congruent to that. So we have 5x plus 29 equals 7x minus 11. 3y plus 15 equals 5y minus 9. All right, so I'm gonna subtract 5x on both sides. I'm gonna add 11 to the other side. I'm gonna subtract 15. Actually, I'm going to subtract 3y. And then add 9 here. So we get 40, this cancels. This cancels. We get 2x divided by 2. So you get x equals 20. We got 24 here. Those cancel. These cancel. You get 2y divided by 2. Oops. That's a 24. And this is 2y. So divide by 2. That y literally looks like the same thing as my 4. All right, so divide by 2, so you get 12 equals y. All right, so now let's do problem set number 3. There should be, I think, so there should be one more problem set, but there's a lot of problems in this problem set. I think I give you 4 problems. Yeah, so 4 problems. Okay, I think, hold on, let's make sure. Yeah, so I give you basically 4 different ones. All right, so What we're doing in this one is we're trying to justify that this is a parallelogram with supporting work, okay? So there's lots of ways that we can do this. We're going to try to use the midpoint formula. There's a few ways to do it, okay? So remember that for if you have a quadrilateral that's a parallelogram, you can prove that the diagonals bisect each other. And if that's true, then you have to have the same midpoint. So if you calculate the midpoint and you find it to be the same, then you have a parallelogram. You can also show that you can also try to show that the opposite sides are congruent, right? Things like that. You can show that the opposite sides are parallel, right? So you can do that as well, that this is parallel this is parallel that, and you can do that by doing slope. Okay, so slope, and then you can use distance, right? And then here you can use midpoint. So you got essentially 3 different methods. And so that's why I have slope, distance and slope, and then you have midpoint. Okay. So let's do midpoint, and yeah, so let's do midpoint. So all right, so to the midpoint, you need to basically do each diagonal. So BD. So what's the midpoint of BD? All right, the midpoint formula, you have to take the 2 coordinates and add them together, okay? And then divide by 2. So A is -2, 3. B is 1, 2, 3, 1, 2, so 3, 2. D is -3, 0. And C is 2, -1. All right, so do it for BD. 3 plus -3. Do it for the x coordinates, divide by 2. Now do it for the y coordinates, 2 plus 0, divide by 2. And then do the same thing for the other diagonal, AC, okay? So -2 plus 2, divide by 2. 3 plus -1, divide by 2. And see if they match up. So 3 plus -3 is 0. 0 divided by 2 is 0. And then 2 plus 0 is 2, divided by 2 is 1. And then this is also going to be 0. And then 3 minus 1 is 2. 2 divided by 2 is 1. So they're the same, right? So they're the same. And therefore, you have to have a parallelogram. So yes, it is a parallelogram. Okay, that's it. All right, so number 2. So now we're going to graph it and then prove it. And we're going to prove it with the slope. All right, so 0, 0 is P. We got 1, 2, 3, 1, 2, 3, 4. This is Q. We got 1, 2, 3, 4. This is 4, 0. That's Y. And Q is 3, 4. And then we have 7, 1, 2, 3, 4. Okay, and then this is S, which is 7, 4. All right, so let's prove that that's a parallelogram. So first, we have to look at the slopes, right? So we need the slopes have to be the same for the opposite sides for it to be parallel. Okay, so we got 1, 2, 3, 4. So it goes up 4, 1, 2, 3, up 4 over 3. Same thing. Let's see here. It goes 1, 2, 3. 1, 2, 3, 4. So it also goes up 4 over 3. So it looks like those two have the same slope. Okay, so the slope of PQ is the same as the slope for SY, which is rise over run. So rise over run. Okay, that's good so far. Now let's do the slope for these ones. Well, we can see that the slopes for these are both flat. So the rise is 0 and the run is 1, 2, 3, 4, right? So the slope for QS is the same as the slope for PY, which is the rise is 0 because it doesn't go up at all. It just goes to the right, and the run is 4. 0 divided by 4 is 0. So they're both the same. So therefore, opposite sides are parallel. So it is a parallelogram. Okay, so therefore this is parallel, and then these are parallel. All right. Okay, so that's how you do the slope method. All right, so now we're going to do the distance and slope formulas for both. All right, so S is -2, 1. R is 1, 1, 2, 3. T is 2, 0. And Z is -1, -2, 1, 2. Oh, of course, Z is right there. Okay. -1, 1, 2, -2. Okay, so let's do the slope first. Let's just count. Okay, so when we do this, we want to do, okay, so rise over run. So it goes, this goes down 2, so -2, and over 1. And then this goes over 1, 1, 2, 3. Looks like this goes down 3. Let me make sure. Oh, I did this coordinate wrong. So this is 2, -2, comma 1. So it's actually, when I draw it, it's actually 1, 2, 3. So it's actually going down 3. Okay, so I was going to say it's not a parallelogram because that failed, but it looks like they're both the same. So the slope for SZ is the same as the slope for RT, and it's rise or run, so -3 over 1. Okay. All right, so now let's do the slope for the other one. Okay. Okay, so this one's going up 2 and then over 1, 2, 3. This one's going 1, 2, 3 and then up 2. Okay, so basically up 2 over 3. So looks like the slopes numbers are the same for them. So the slope of SR is the same as slope of ZT, which is up 2 over 3. All right, so the opposite sides are parallel, so it has to be a parallelogram. But now let's do with the distance formula, okay? So now we're going to say, okay, SZ is the same as RT. So how do we calculate with the distance formula? Well, that's the square root, and the square root, and then you take the two numbers squared, okay? So you got 2 squared plus 3 squared for the red numbers, okay? So we got 2 squared and then 3 squared. And then you add them. Oh, SZ and RT. Sorry, I was using the wrong numbers. -3 and 1. So -3 squared and then 1 squared. All right, and then they're the same numbers, -3, 1, -3, 1. So 3 times 3 is 9. 1 times 1 is 10. So you get square root of 9 plus 1, which is square root of 10. So they're both the same. They're both congruent. And then let's do the same thing for SR and ZT. So it's the square root of rise squared plus run squared. So 2 squared plus 3 squared. 2 times 2 is 4, and then 3 times 3 is 9, so we get square root of 13. So the opposite sides are congruent, and then they're also parallel. So by both methods, yes, it's a parallelogram. Okay, all right, so let's look at, so we got one more, and then for the midpoint formula. Okay, so we get W is 2, 5, 1, 2, 3, 4, 5. So this is W is 2, 5. R is 3, 3, 1, 2, 3. Y is -2, 1, 2, 3. And N is -3 and 1. -2, -3. Just want to double check my coordinates here. 1, 2, 3, 1, 2, 3. 1, 2, 3, 4, 5. Okay, so let's go ahead and graph it. And let's do this. This looks a little odd, so it might not work, right? But we're going to do the midpoint. So let's do the midpoint of the diagonal. So WY. So the midpoint of, let me just write it out. Midpoint of WY. Again, add the coordinates, divide by 2. Okay, so the coordinates of W, let me write those out again because they're not written well. 2, 5. So 2 plus negative 2, 5 plus negative 3, and then divide by 2. We'll do that math in just a little bit. Now let's do it for NR. So negative 3 plus 3 divide by 2, and then 1 plus 3 divide by 2. Okay, so we got 2 plus negative 2 divided by 2 is 0. 5 plus negative 3 divided by 2 is 1. Negative 3 plus 3 divided by 2 is 0. 1 plus 3 divided by 2 is 2. So they're a little bit off. They're 0, 1 versus 1, 2. So they're not the same. Therefore, it is not a parallelogram. All right, that's going to do it for the video, guys. Hope you found this useful. And as usual, I'll see you in the next one.